Imagine that you're dining in a high-end restaurant in Taipei 101. Suddenly, everything starts shaking. You and your friend are very nervous. What happened? Earthquakes occur when tectonic plates shift. This sudden burst of energy sends seismic waves shooting in all directions. These waves can violently shake buildings both up and down and side to side with enormous force. It's this forceful shifting that actually causes stress on the buildings to the point of collapse. But are earthquakes the one and only threat to the buildings? The answer is absolutely no. Here's the situation again. Have you ever heard the word vortex shedding? This happens when the wind blows across tall buildings. Vortices can form coherently on the sides of the buildings buffeted by steady winds, exerting alternating force on the structure. This generates low-pressure zones at the downside of the structure, giving rise to fluctuating force acting at different angles to the wind direction. And the most important, when the natural frequency of vibration of the tall building equals the frequency which vortices are shed from the building, the horrible resonance sets in, and the building may experience large crosswind oscillations. But as we live in Taiwan, struggling with numerous earthquakes and typhoons every year, we realize a fundamental truth. Earthquakes and wind don't kill people, buildings do. That's why engineers have spent a lot of time wondering how to make buildings safer. The most common and efficient way to strengthen the buildings is to add some special equipment called damper. Damper is a mechanical or hydraulic device designed to absorb impulses. It does this by converting the kinetic energy of the shock into another form of energy and then dissipate.
And now, we're going to introduce the most famous damper in Taiwan, which is also our topic today. A way to reduce shaking, the tuned mass damper. Let's just call it TMD. TMD can be broadly split into two types, passive TMD and active TMD. The two types of TMDs react differently while winds and earthquakes occur. The passive TMDs are tuned with the first mood of the structure. Accordingly, when the specific frequency is excited, the damper will resonate out of phase with the structural motion. The active TMDs work with feedback control of the response. This could be done by real-time monitoring of the structure's response and generating a force known as corrective control force. Both PTMD and ATMD have their pros and cons. ATMD has more appropriate efficiency and structural displacement response reduction compared to PTMD, in spite of high cost of installation and conservation. Based on different considerations, different types of TMDs are used. For example, PTMD is set in Taipei 101 and ATMD is used in Kaohsiung 85 Sky Tower.
TMD is set inside many skyscrapers and slender towers worldwide. It is commonly used for mitigating excitation mechanism for winds and earthquakes. And today, we are going to focus on the TMD in Taipei 101 Tower. We just talked about TMD, but what is the TMD? TMD is the abbreviation of tuned mass damper, and it is a large, massive block which is usually mounted on the top or near the top of a tall building. The system consists of a mass, springs, and damping devices. Its frequency can be tuned to match the predominant vibration frequency, usually the first model frequency, of the main structure. To be specific, we'll introduce the TMD system in three parts. Let's talk about the mass first. The diameter of the TMD is about 5.5 meters, and it is composed of 41 layers of solid steel plates. The weight of this thing is about 600 mounts. It is very gigantic. The mass block is hung by 8 cables at the 92th floor with a diameter of 8.9 meters. To ensure its flexibility and extend the service life, every steel cable is composed of over 2,000 independent small steel wires. The cable is extremely rigid. And how strong is it? It can hang the whole mass block only by 2 cables, which also means the safety factor is 4. The mass ratio between the TMD and the building is the crucial parameter in the TMD design. Generally, the mass ratio is between 0.5% to 2.0%. There are 8 primary hydraulic viscose dampers set under the mass block. They are designed for absorbing the energy that is produced by the mass system. In addition, a bumper ring which can limit the amplitude of oscillation is set under the mass block.
Let's talk about the reasons make the TMD work. The building generates resonance when it undergoes environmental excitation, such as winds, earthquake, etc. At this moment, TMD resonates in the opposite direction to offset the energy. Why does it work? Because the TMD has been set to the same frequency as the predominant frequency of the building. To illustrate, we can simplify the system as a simple pendulum. Because of the small displacement, we can assume that it is a simple harmonic motion. Let's look at this equation. The period and the frequency only depend on the length and the gravity. The natural vibration of Taipei 101 is 6.8 seconds. After being calculated, the length of the TMD should be 11.5 meters to meet the same period as Taipei 101. That's why the TMD is set between 5 floors.
After introducing the method of absorbing the vibration, I think you must have a further comprehension about this. Also, TMD is commonly known in Taiwan. It is not the only structure to reduce the shaking. There are other methods such as FVD. We believe that there are more techniques for us to develop in the future.